Hello everyone, it's my honor to give the presentation in EAI ChannelCom 2021 International Conference on Communications and Networking in China. My name is Xiaoxu from Beijing University of Posts and Telecommunications. The title of the paper is Non-Coherent Receiver Enhancement based on Sequence Combination. There are 5 parts in my presentation: introduction, system model, method, results, and conclusion. First is part 1, introduction. Physical uplink control channel (POCCH) is one of uplink channels in the physical layer of the 5th generation wireless communication. Though the 5th generation develops at a high speed, the space propagation loss is high, which brings challenge to the coverage of the 5th generation. Therefore, it's necessary to study the 5th generation coverage enhancement scheme. POCCH format 3 with 11-bit UCI need to be enhanced according to the 3rd generation partner project reference, which provides the baseline performance. There are 2 methods for UCI to be transmitted in POCCH. One is coherent transmission based on demodulation reference signal (DMRS), and the other is non-coherent transmission without DMRS. It's well known that the performance comparison between 2 methods depends on operating SNR region. In high SNR region, coherent transmission is better. However, in low SNR region, non-coherent transmission should have better link level performance. Therefore, considering coverage scenarios, DMRS-less non-coherent transmission can be adopted as a potential technique for POCCH coverage enhancement. For specific solution of DMR-less non-coherent transmission, there are already some studies. One is long sequence design at the transmitter. The other is sequence combination design composed by 2 short sequences. 2 different transmitters use the same receiver, non-coherent receiver. The latter one reduces the resource consumption. However, the problem is that the non-coherent receiver based on sequence has high reliability, but with high complexity, which limits the utilization of non-coherent receiver. So, in this paper, non-coherent receiver enhancement based on POCCH sequence combination is proposed. A long sequence is composed by 2 short sequences at the receiver. The main idea of non-coherent receiver enhancement in this paper is dividing the received signal into 2 parts and choosing several candidate sequences of each part to determine the target sequence combination. The computation complexity can be reduced significantly with smaller solution domain at the receiver. Next, the second part, system model. The system model includes transmitter and the receiver. For the transmitter, one approach to generate sequence for DMRS POCCH is reducing the sequence. The sequence is generated by the formula in this slide, as we can see here. The low PAPR sequence R is defined by a cyclic shift alpha of a base sequence Rn. M is the length of the sequence. Multiple sequences are defined from a single base sequence through different values of alpha and delta. Okay, look at the picture in the slide. When transmitting 11 bits UCI, there needs 2048 sequence combinations to represent UCI. The sequence is selected from a sequence pool S. The number S can be calculated by the formula in this slide. We can calculate that the S is 30 is 65. Two sequences are selected from the sequence pool S. They map to the time domain and frequency domain. Two parts, each with 7 symbols, carry two sequences to transmit UCI bits. Okay, at the receiver side, a sequence detection is performed and the UCI payloads could be determined for a long sequence. The non-coherent receiver adopts correlator to detect the signal, which is also called blind detection. The procedure is shown in the slide. First, the received sequence is correlated with all possible sequences in the sequence pool and the module is taken. Then, the candidate sequence with the largest power value is determined as a sent sequence. Finally, the index of the sequence in the form of decimal is converted to the form of binary. For each correlation, the received sequence is correlated with long sequence composed by two short sequences in the sequence pool. This detection method has high accuracy but high complexity at the receiver. As for the performance metric, in addition to 1% BLER performance metric, without the discontinuous transmission DTX detection is necessary, and when is considered, the performance metrics are shown in the slide. They include 1% DTX to ACK error rate, 1% ACK misdetection error rate, including ACK to NACK and ACK to DTX, and 1,000th NACK to ACK error rate. Okay, it's the third part, method. In this part, the non-coherent receiver enhancement based on pure CCH sequence combination is proposed. The design of enhanced receiver is shown in this slide. The received signal can be divided into two parts and correlated with sequences within the sequence pool respectively at the receiver without being correlated with all possible sequence combinations. In this way, the computation complexity at the receiver can be reduced. Firstly, the receiver divides the received signal into two parts of the same length. For each part, the half of the received sequence is correlated with 65 short sequences, and the module value U is taken. The specific calculation is given in the slide, as we can see here. Secondly, the 5 largest power values, which represent 5 candidate sequences S11 to S15, can be retained. Thirdly, one correlation value from one of the 5 candidate sequences in the former part and the other correlation value from the latter part are added together. The value is calculated by the formula given in the slide. Determine whether the selected sequence combination is a valid one, representing UCI bits or not, judging the sequence combination until the valid one is found. Finally, it's the same as the previous part 2. The index of the sequence combination in the form of decimal is converted to the form of binary. After we introduce the design of enhanced receiver, the performance of this design should be evaluated. The definition of the solution domain is given here. It means that there are several kinds of alternative sequences at the receiver. The size of the solution domain on conventional receiver and enhanced receiver can be evaluated and analyzed. For example, the solution domain size of the conventional one is 2048, which is larger than that of the enhanced one with 25. The bigger the solution domain is, the more complicated the computation is, which can be expected. As for the complexity of conventional non-coherent receiver and enhanced receiver, the specific complexity is shown in the slide. C represents number of candidate sequence for each part at the receiver. M represents number of resource elements in the POCCH. When the number of candidate sequences is increased, the complexity is increased too. The complexity of enhanced receiver is about 3% of that of original receiver. To sum up, the statistics of complexity verifies that the enhanced receiver reduces complexity of non-coherent receiver dramatically, but it's too complicated to evaluate the reliability of the scheme in theoretical calculation. Therefore, the reliability of the scheme needs to be evaluated by computer simulation. Okay, it's a fourth part. Results. In this section, simulations are performed to evaluate the detection performance of non-coherent receiver enhancement based on POCCH sequence combination. The simulation parameters are shown in the slide. The baseline includes POCCH Format 3 in release 16 with coherent receiver, a long sequence scheme, and a sequence combination scheme with non-coherent receiver. For the first simulation, the results of enhanced receiver based on POCCH sequence combination with different candidate sequences are shown in the slide. C represents number of candidate sequence for each part, which is mentioned in part 3. The horizontal axis represents the number of OFDM symbols, and the vertical axis represents ISNR of 1% BLER metric. The performance of the enhanced receiver with turn candidate sequences is better than the others. Compared with conventional receiver, the enhanced receiver has 0.2 to 0.4 dB performance loss. The enhanced receiver reduces computation complexity with slighter performance loss. Comprehensively considering latency of choosing best candidate sequence combination and reliability of enhanced receiver, turn candidate sequences is the best choice. For the second simulation, the enhanced receiver needs to be compared with the baseline. The performance of schemes based on sequence is much better than POCCH Format 3 with coherent receiver, and the enhanced receiver has 0.2 to 0.4 dB performance loss compared with non-coherent receiver. For the third simulation, DTX detection needs to be considered. As we can see in the slide, the result is similar to the simulation result without DTX. To sum up, the simulation results show that turn candidate sequences is the best choice considering latency of choosing candidate sequence, combination, and reliability. The complexity of the enhanced receiver is verified in part 3. In this part, the reliability of the enhanced receiver is evaluated. The enhanced receiver reduces computation complexity with slight performance loss with or without DTX detection. Okay, as the final part, conclusion. In this paper, non-coherent receiver enhancement based on POCCH sequence combination is proposed. For POCCH coverage enhancement, first, in theory, the enhanced receiver reduces the size of solution domain and computation capacity compared with conventional receiver. Second, according to the simulation results, the enhanced receiver has slighter performance loss compared with conventional receiver, whether DTI detection is considered or not. Finally, considering complexity, latency, and reliability, the number of candidate sequences of each part can be determined due to specific scenarios. Okay, for the future work, in addition to the design of sequence combination, there may exist better methods to generate sequence. For the receiver, the features of sequence can be used to reduce complexity. Okay, my presentation is over. Thank you for your listening.